Gettysburg Seminary presents the Seminary Explores podcast. Conversations on faith, art, people, politics, theology, life, and more, with voices from around the corner and around the globe.
Hello, welcome everyone to Seminary Explores, the podcast put out by Gettysburg Seminary. My name is Kristen Johnston-Largen, and I am here with a very special guest today, Dr. Michael Wedlock, who is chair of the chemistry department and associate professor of chemistry down at Gettysburg College. Welcome, Michael.
Thank you. It's nice to be here.
It's great to have you with us. Well, again, we are in a series of talking to scientists because we got this wonderful grant to talk about science in the seminary curriculum. And I thought, let's talk to a chemist because I don't know anything about chemistry. And so I wonder if we might start by hearing a little bit about how you came to chemistry and what your work is in particular.
Sure. So I came to chemistry the way I think most people come to chemistry, in that I had a really good high school chemistry teacher. So I think at the college, I can't remember ever having a chemistry major who said I had a bad high school chemistry teacher, but
that's
I love
very
chemistry anyways.
okay.
High school chemistry teachers are kind of the backbone of our profession.
Oh, that's lovely.
And so I had a great chemistry teacher in high school and decided to major in chemistry in college, and fell in love with molecules and molecular orbital theory, which is sort of a small branch of chemistry, and just kept on. So went through college and then graduate school and postdoc and became a professor.
Yeah. How big is your department at the college?
So we have 8 full-time faculty and then half a dozen or so lab instructors who help us out by teaching the introductory lab courses and the organic lab courses, and safety officer, administrative assistant in the department. So,
is it when you think about all of your areas of specialization, is it pretty broad in terms of what people do? I mean, what are the kinds of work? What's the kind of work that people do in your department?
Yeah. So the nice thing about chemistry is that they used to, and you don't hear it so much anymore, but it used to always be called the central science.
Oh, nice.
Because it kind of bridges the gap between physics and biology, and it's most areas of science have some relationship to chemistry, and so we have people in our department who work on everything from gold nanorods, which are tiny little rods made out of gold atoms.
Really?
Which have kind of interesting properties because they're sort of halfway between molecules and what you would think of as a solid. So it's kind of a different range of space that chemists haven't thought much about. We have somebody who does biophysical chemistry, so she thinks about kind of modeling cell walls. So it's very much chemistry in the realm of biology.
Okay.
I focus mostly on using lasers to break apart small molecules that have 4 or 5 atoms. So I'm kind of the far opposite end, but Shelley Fry and I both teach the same course sometimes. So,
I bet that's fun.
So that's nice. And we have another biochemist who works on genetic issues, and some synthetic chemists who build molecules that have interesting properties, catalysts, or they have cool-looking shapes if you draw them out. So there's a huge range of interest in the department.
Well, you said I love to think about chemistry as the central science. Theology used to be called the queen of the sciences, and we still really kind of cling to that, right, with a death grip. But why is that? I mean, what is chemistry? I mean, you've mentioned molecules. What's a molecule? I mean, just assume I know nothing, because I don't.
So a molecule is basically... So the way that it's usually explained is if you take a piece of matter, so say a chunk of ice, and you kept cutting it more and more finely, right? Eventually, right, ice is made out of water. Eventually, you would get down to the point where you had a single molecule, which would have an oxygen atom and 2 hydrogen atoms in it. If you cut that any further, it wouldn't be water anymore. It would just be separate atoms. But basically, chemists look at molecules, which is sort of a molecule is an assemblage of atoms, and it's kind of the smallest piece that has a chemical identity that would work in a chemical reaction the way a chemical would. Below that, you get to sort of atomic and nuclear physics. And
okay, is that then why you would say chemistry really kind of bridges the physics-biology divide? Because, like you said, anything smaller than a molecule sort of belongs to physics, and stuff that's a lot bigger than molecules belongs to biology.
That's exactly right.
Excellent. That's a great explanation to me. I just never even thought about it that way, but that makes all kinds of sense.
Yeah, chemistry has sort of been creeping out. So there used to be atomic and molecular physics, and that's sort of been consumed by chemistry. And more and more biology tends to be molecularly oriented, because now that people, by now, I mean in the last 40 or 50 years, that people are interested in DNA. DNA is a molecule, so you can apply a lot of chemistry to that.
Oh, sure. Okay.
Biology kind of has sort of a molecular end now that it didn't, say, 100 years ago. So chemistry's infiltrating the biological world.
Can you? This is probably a ridiculously long and complex question, but can you tell me a little bit of like the history of chemistry? I mean, how did chemistry come to be as a science?
Sure. So chemistry kind of initially grew out of alchemy in some ways.
Oh, okay.
So alchemy has kind of this complicated history where some alchemists were just coming up with ways to refine metals, basically, and other alchemists were coming up with ways to cheat people out of money by saying they could turn lead into gold.
Sure.
And so that history developed, and basically it involved people, trying to learn some things about the world by thinking about molecules without having any concept that molecules existed, because it was far before people had any idea of that. And then towards the end of the 18th century, during the Enlightenment, people who were interested in chemistry decided that alchemy was a bad, scary thing that we didn't want to talk about anymore. And so alchemy became chemistry kind of in the late 18th century, and people started to get a better idea that there were things like molecules, and kind of up through the 19th century developed the idea that atoms existed and got a better grip on what molecules were. And so, finally in the 1920s, when quantum mechanics developed, you actually had people that had some reasonable idea of what, say, a chemical bond is. So chemistry became chemistry over a long period of time, starting with turning lead into gold and ending up with quantum mechanics.
Wow, that's really amazing. Well, the one thing I think that when people hear chemistry, they think of, even though they don't know much about it, is the periodic table. Mm-hmm. What is the periodic table, and why is it organized the way that it is?
So the periodic table contains an incredible amount of information, and basically it was created by Mendeleev, who was thinking about the way that different chemical elements behaved. And
what was that, like 19th century? Or?
Yeah, 19th century, kind of I want to say 1870s, but that could be...
Say it with confidence, and I will agree with you.
It's the listeners I'm worried about. So
that's true.
I don't want some kid to get marked down on a high school chemistry test because this professor from the college doesn't know when the periodic table was developed. So
okay, we'll leave it vague.
So check those facts.
Okay. But that's always a good idea anyway.
But Mendeleev had seen that particular elements had similar properties, and so he was sort of looking for a way to organize the elements based on, say, how they reacted with other elements. And
what's an element?
So an element is so if you look at an atom, an element would be an atom that has a certain number of electrons, would be one way to explain it. So a hydrogen atom will have one electron, a helium atom has two electrons, and that's kind of the way we actually, just to clarify, so it's really the number of protons, but if the atom's neutral, it'll have the same number of electrons and protons. So,
okay. I know you're all concerned about these.
I know.
About these kids listening at home.
Another lie to some poor high school student who is going to fail chemistry because
it's a lot of pressure.
I lied to her on the radio. Right. So an element is an atom that has a particular number of protons, and if it's neutral, it'll have the same number of electrons.
Okay.
And so so hydrogen has one proton, helium has two, and the periodic table, what you do is you kind of organize the all the elements by sort of their similar properties, mostly how they react chemically. It was sort of kind of the initial way that it was developed, and now it has to do with, since we have a better understanding of the atom, kind of organized by the number of electrons they have and how the electrons are organized in the atom.
Okay, and why does that matter?
So it's handy because you can atoms that have so the electrons in an atom are kind of arranged in shells, almost like an onion.
Okay.
And atoms that have the same number of electrons in their outermost shell tend to behave in a similar way chemically. So, for example, the noble gases, helium, neon, argon, xenon, krypton, all have a full outer shell, and so they tend to be very unreactive. So they're called the noble gases because they don't react
play
chemically
with anybody.
Exactly.
Okay. They're snotty. We could
Right.
also call them the snotty gases.
Sometimes, but
It's probably
not in textbooks.
Okay. And high school students, not you
Right.
either on your test.
Exactly.
Okay.
And other groups of elements have similar sorts of behaviors. So the halogens all have 7 electrons in their outer shell, and so they tend to, so fluorine, chlorine, bromine, iodine, they tend to have similar chemical reactions and similar chemical properties. So basically the similarity in the properties comes from having the same number of electrons in this kind of outer shell, and so that's the way that things get organized in the periodic table.
Okay, and so when you look at the periodic table, then you can predict how certain things are going to react when they're in this kind of experiment or when they're combined with that kind of
to a first cut, anyways.
Okay. But I want to ask you one more thing, and then we'll move to kind of a little bit of the bigger picture. So most of us, if you went to college, either you yourself suffered through, or you know friends who suffered through organic chemistry. That's like everybody that has the reputation, right, as being the hardest course in a college curriculum. What is so hard about organic chemistry? What's organic chemistry about? And is it true, or is it overblown?
See, I don't teach organic chemistry, so I have to...
At some point, you had an organic chemistry class,
I did,
imagine.
but I'm trying to be respectful of my colleagues.
Okay, there we go.
Teach organic chemistry. So organic chemistry is basically the chemistry of molecules that contain carbon. So it's called organic because initially the organic molecules were things that you got from sort of living creatures, plants or animals.
Oh, okay.
Most of the important molecules in biochemistry are all built out of carbon with some oxygen and nitrogen and hydrogen added in. But carbon has this interesting property that it can make an enormous number of molecules, and most of the other elements will have a much more limited range of ways they can bond together. But carbon, you can make everything from methane gas, which has 5 elements, all the way up to DNA, which has an enormous number of atoms.
What's the unique properties of carbon that it can do that?
It has to do with the way that with kind of the energy levels of the electrons in the atom, and so it just works out well.
It just plays well with others.
It plays well with others, right?
And we all know people like that also.
Right, in ways that are very hard to explain without a great big chalkboard.
All right.
But it's one of those things where, in science fiction movies, sometimes they'll come up with, alternate worlds where everything is made out of silicon and things like that.
Right.
And that's the closest you could come to a world that's not made of carbon, but even that doesn't really work. Carbon is just unique in that aspect.
So, is that true? Is every living thing made out of carbon? Is that...
Mm-hmm. Everything is made out of carbon.
So. Everything is made out of carbon. Huh.
Right, every living thing.
Yeah. Plants, animals,
all of it is all carbon-based.
All carbon-based. So it sounds like there's a lot to learn in organic chemistry then.
Right, and that's what makes it hard, is that there's a lot to learn. So, carbon, because it can take so many. It can be in so many molecules. Has a huge number of reactions it can undergo, and a lot of organic chemistry is understanding all of those chemical reactions and how they can happen and why some of them happen and some of them won't. And so it's a huge field to cover, and it's different from so typically in an introductory chemistry class it would be much more kind of calculation focused, a lot more calculating the pH of solutions and things like that. And there's much less of that in organic chemistry. So in some ways it's a very different focus from what students would have seen in their first year. And so you kind of, if you were a whiz at introductory chemistry, there's no guarantee that you'll be great at organic chemistry.
And that's a learning curve right there.
So it can be a challenge for students.
Well, this is actually a great point to kind of step back and say, why does all of that matter? So you're talking about these experiments. Does it react this way? So what? I mean, what are the kind of things then that especially if we're talking about living things, right? What is that? How does that help us understand the world better?
Right. So so one of the nice things about chemistry is that part of the job of chemistry is to understand the world, but then the other nice thing about chemistry is that you use it for all sorts of practical things. So if you're interested in developing a drug, and a chemist would be the person who would synthesize the molecule that you're going to use as your drug test. So basically, drug companies are chock full of chemists because the chemists are the ones building the molecules. If you're interested in painting your house, there are chemists who are developing the paint. If you're
so again, for example, like in that, so to see what kind of what the solution of the paint needs to be like, so it adheres to the wall well and takes color well. Right, so it adheres to the wall,
so the color lasts.
Okay.
All of that is chemistry. People who do archaeology now, so they'll often do carbon-13 dating and chemical analyses of residues. So my husband is a museum curator who works on Chinese export porcelain, and he's collaborates now with a couple of chemists because they can use their analytical equipment to analyze the glazes on the porcelain that he works with.
Wow.
And that helps him determine if pieces are genuinely old or if they're fake.
Okay.
So, every chemistry is kind of everywhere. So it's anything that has to do with molecules, there's probably a chemist touching it in some way.
Why is organic chemistry, again, to kind of hone the point, so in a pre-med curriculum, right, you always have to take organic chemistry?
Right. It's basically because, the drugs that doctors would administer will typically, for the most part, be organic molecules. Organic chemistry is kind of the basis of biochemistry. So proteins are essentially enormous organic molecules. DNA is a big organic molecule. So if you want your doctors to understand biochemistry, they've got to understand some organic chemistry before they can really understand what's going on in biochemistry.
You talked about synthesizing molecules. If we can synthesize molecules, why do we still need to do like animal testing, or even why do we have to do testing on people? Why can't we just...
Well, because part of the problem is people are really complex. And
that is so true in so many ways.
That's undoubtedly something you're familiar with up here at the seminary. People are very complex, and so you can synthesize a molecule, but it's very difficult to tell how it will act in a particular situation without some sort of testing. So, my area is physical chemistry, which is kind of the opposite end of the field from biochemistry. But my understanding, anyway, is that biochemical mechanisms in living organisms are so complex that it's very difficult to tell how a particular molecule will interact with all these different systems without actually testing it on a living system.
Okay, so we're not to the point yet where chemistry can help us.
Right, you can predict some things, but it's not. We don't have a sort of a simple chemical model for a human being yet.
Okay. What would you feel like would have been the most substantive or kind of exciting changes in the last few decades in chemistry, would you say? Or is the field moving in a sort of interesting direction? Or
yeah, the field's moving in kind of lots of interesting directions. So one of the it's hard to even know which to pick. Actually, one of the things that has been really influential on chemistry is the development of more powerful computers, because it has, and so this kind of reflects a little bit on my background in physical chemistry, which is sort of the interface of chemistry and physics. But the computers allow you to do much more in the way of powerful calculations to predict chemical properties and how chemicals will react. But they've also made it much easier to automate instrumentation so that you can, so for example, if you have a clinical lab at a hospital where they're doing chemical tests, you can do those tests much more quickly now than you could before.
Okay.
So now if you send blood samples to the lab, you may know back in an hour what would have taken a couple days to find out before. So,
Sure.
So advances in instrumentation, the biochemistry, I think, has made huge strides over what it had. Material science has gotten really interesting. So kind of looking at...
What does that mean, material science?
So it's basically taking chemistry and applying it to things that you would make other stuff out of. So it could range from everything. So like I mentioned before, one of my colleagues in the department works on gold nanorods, so sort of material at a scale between what you would think of classically as a molecule and the bulk.
Okay.
But also people look at, say, developing new plastics that have all sorts of interesting properties, or developing solar cells so that you can collect sunlight more efficiently.
Okay.
Developing all sorts of new materials that have different metallurgical properties.
Yeah.
There's kind of exciting stuff going on in chemistry all over the place.
Well, this is probably not a fair question, but I'm gonna ask it anyway. I mean, when we had talked before we started kind of live on the podcast about how ignorant I think most of us, and certainly those of us who are public ministers are about chemistry. I mean, what do you think is important for us to know? What do you think would be helpful, or that would kind of make a difference in terms of? I know it's not really fair, right? It was a totally just kind of throw you on the spot kind of question. I mean, I guess I'm going back to the idea of carbon. I mean, so I'm giving you now some time to think. So this is my filler. I'm
See, I'm going to listen to you instead of thinking. That's going to be the problem.
Well, I was just when you think about our similarities down at this kind of molecular level with all life. I mean that to me is actually a fairly profound theological statement, and so I was kind of just playing out with that sort of even to think about how that's true. And so one of the things that I've been appreciative about when I've talking to you and talking to some of your colleagues is so if I were to answer my own question only in the most general sense, like science in general, is it really does tell us some very specific concrete things about the world that undergird and shape the kind of general pronouncements we make. So when we say, yes, we're actually in relationship to everything. Well, I can say that on a kind of a theoretical or even a spiritual level, but actually talking to you reminds me of how on a material level I can actually talk about something like that, and for me that's a general answer, but I was just thinking in terms of as you understand your own work and again kind of the big picture, so what life that you live, why you think it matters.
Right. So I think it sort of one of the I think one of the ways that people understand and appreciate the world is to see the beauty of things. And so on one level, people look at a sunset and think, oh, the sunset is beautiful, it's amazing. But I think one of the nice things about chemistry and science in general is that it can help you go beyond saying, oh, the sunset is beautiful, to saying, okay, I understand why the sunset is more beautiful on days when it's hazy than it is on clear days. Right. And it goes back to the way light scatters and things like that. And so I think to the extent that you find beauty in the world and the universe, I think for many people it helps them appreciate that beauty more if they understand it. And for some people it's like, oh, you've ruined sunsets for me because I just want to see the beautiful sunset, and I don't want to think about rays scattering at this. But I think that I think that understanding how things work is actually powerful. So kind of in your daily life, if you think, okay, the reason that somebody is sick and the way that we can make them better is because of this particular chemical reaction that's happening in their body, I think that that is not only a more powerful way to help them get better, but it also, I think, helps you think more clearly about the universe than just thinking, oh, they're sick because something bad is happening to them. And for whatever reason, something bad would happen to somebody. And so I think I'm an educator, and so I think people tend to be served well by knowing more about what's going on around them. And so I think chemistry helps us understand what's going on in the world in a way that both allows us to understand it and also to make people's lives better in ways that reduces their pain, makes them less sick, makes them more comfortable. Keeps them from freezing in the winter or dying of heat in the summer. And so I think one of the great things about people used to talk about better living through chemistry, and I think. I
think chemists used to talk about better living through chemistry.
I think it was entirely a chemical company that came up with that. But I think part of chemistry is a powerful tool for helping to understand the universe. So I think to the extent that your life is enriched by understanding the world around you more, I think that chemistry is a useful tool for that. At least that one aspect of the world that is described by molecules.
I think that's fabulous. And again, I would like to think that of all people, I mean, not we all have different reasons for wanting to understand, but Christians in particular, right? We should want to understand the world because we believe that God made it, loves it, cares about it, continues to be active in it. And so for me, even to hear you describe a sunset, I mean, there's the sense of how wonderfully and intricately. Is that right? I can feel like it's not. Intricate. No, it's not the right word. What's the word I'm looking for? I can't believe I can't say it. Anyway, this happens on the podcast. Fine, we'll go with that.
Intricately.
Intricately.
That's what it is. Intricately.
Oh my gosh. Yeah. Well, maybe we can get that taken out, edited out of the podcast. We'll see. But so as a Christian, for me, I mean, that's something that positively informs and challenges me. And and obviously you don't have. I mean, I think you've made it clear. I think it's great for everybody, that kind of understanding. But I think for me, obviously, as we're here at the seminary trying to talk to people about why science is important. I mean, you've said it so well. I mean, that's exactly why it's important. So yeah, fabulous. Well, our time is up. Thank you so much for being here. I've really enjoyed the conversation. Yeah, and
it's nice to come up the hill once in a while. And
you are welcome
see
anytime.
The view from on top of the ridge.
We get great sunsets from up here. Thank you so much. Again, this is Kristen Largent with Dr. Michael Wedlock from the college, and we've just had a wonderful conversation. Thanks so much.
You have been listening to The Seminary Explores from historic Seminary Ridge in Gettysburg, Pennsylvania, a production of Gettysburg Seminary. We invite you to visit our website at www.ltsg.edu. Opinions expressed on this program are not necessarily those of Gettysburg Seminary or the Evangelical Lutheran Church in America.